Hey there, crew, and welcome to another episode in the Geology 101 Physical Geology video series. I'm Geology Professor Shawn Willsey. Thanks for joining me today. Today, in episode 16, we're going to look at metamorphism and metamorphic rocks, a continuation of what we studied last time looking at the sedimentary rocks, just moving on to another group of rocks to round out our study of the three rock types. In our future episodes, we'll be looking at concepts of geologic time and different processes that related to things that happen at the surface, like rivers, streams, things like that. Remember that this video series is modeled after my college course, so it's the same content and curriculum you're getting right here, and you can supplement these videos if you need more of a hands-on or you need to see the rocks in a little bit more detail than what I'm providing with these lectures. I do have video links under the video description where you can look at some of the rocks in a little bit more detail, learn how to tell the differences between the rocks, and you can also supplement this with some of the field-based videos I've done as well. So let's get right to it. We've spent weeks looking at the igneous rocks and volcanic activity related to magma cooling and crystallizing. We've looked at concepts related to weathering and the erosion or transportation of sediments that eventually get deposited and become sedimentary rocks. And now we're heading back underground to look at what happens to rocks of any type when they are subjected to temperatures and pressures, the metamorphic realm of things. And so this is the part of the rock cycle we're going to focus on first. But first, let's do a quiz question. Let's start off with a quiz question right here off the bat. So here's your statement, a simple true-false statement. Metamorphism occurs when rocks are melted by heat and or pressure to form new rocks. So take time to mull that over, maybe have a conversation with your pet or yourself or your friend, and see what you think. Go ahead and pause the video if you need to. Okay, let's go ahead and dissect this. So again, the statement is metamorphism occurs when rocks are melted by heat and or pressure to form new rocks. Well, for a true-false statement to be true, it needs to be completely true. And as you read this statement, it sounds pretty good, like it's very compelling, but the one word that messes it up is right here, melted. Metamorphism does not involve melting rocks. When we melt rocks, we take them back into magmas, essentially, and that's taking it back into the igneous realm. So this is a question I give my students right off the bat, and they oftentimes miss this one as well. So if you missed it, don't worry. Just learn from your mistakes. This is a good learning opportunity. As we're going to see, metamorphism is a solid state change. It does not involve melting. So this is a false statement. So changing one rock type to another with the presence of heat, time, maybe some pressure, maybe some fluids, that's what metamorphism is. So we're changing one rock type to another. Meta means change, morph means form. And this again is a solid state change. There is no melting of rock involved in the metamorphic world. If you start melting rock back to magmas, then you're back into the igneous part of the rock cycle. And the changes for metamorphism can be kind of slight, what we sometimes call low-grade metamorphism. For example, a shale being metamorphosed into a slate involves fairly low temperatures and pressures and not a very pronounced change in what the rock looks like after that process. Or it could be more extreme in a high-grade metamorphism event where we really substantially change the texture and characteristics of the rock due to metamorphism. So when we talk about the original rock that existed before it was metamorphosed, that's what we call the parent rock, although you sometimes hear the word protolith. I prefer parent rock, so that's the one I'm going to use. That's the rock that existed before metamorphism occurred. So in this case, we have a limestone. You can maybe pick out some of these little star shapes or rounded stems of crinoids in here. So this is a limestone that has chunks of invertebrate fossils in it. This formed on the bottom of the ocean. And over here on the right, we have what it turns into when it becomes metamorphosed. This is a marble. So limestone is the parent rock of marble. And limestone, as we've learned, is composed of calcite. It's completely made out of calcium carbonate in the form of these little organic material, these shells and such. But when this gets heated up, to high enough temperatures and pressures, this calcite recrystallizes. It's no longer stable at those elevated temperatures and pressures as these little shells, and all the calcite recrystallizes into the marble we see over here. And so sedimentary or metamorphic rocks, in terms of their parent rock, it might be originally a sedimentary rock like we talked about with the limestone, could be an igneous rock, or it could be a pre-existing metamorphic rock. And knowing a little bit about what you started with, if you can figure that out, and sometimes it's not obvious, that might tell you a little bit about how high the temperatures or pressures needed to be to metamorphose the rock. So for example, it might not take a lot to change a limestone into a marble, but if we start with something like a granite, which already forms at high temperatures, then it might take substantially higher temperatures or maybe more pressure to really exert some sort of change in the rock. And that's fundamentally what we're doing here. We're changing some aspect of the rock in order to call it a metamorphic rock. The rock has to change, usually in terms of its texture. It's usually not much of a compositional change. It's usually more a recrystallization and the characteristics of the rock. So we talked about heat a little bit. What exactly are the ranges of heat in terms of metamorphic temperatures? And so anywhere from about 200 to 800 degrees Celsius or 400 to 1500 degrees Fahrenheit. So these are temperatures you can replicate in your kitchen oven. But before you go out and try to bake a limestone into a marble, realize that time is another important variable here, that it takes an incredible amount of time with those temperatures in place to get the molecular migrations and the things happening at the atomic level in order to form the recrystallization of the rock into a metamorphic rock. So it's a big range of temperatures because we start with rocks of various compositions. So there's lots of different rocks that might be our parent rocks. And then as we push the upper end of this temperature range here, 800 or 1500, that's where we're starting to get back into the melting phase. That's where we're starting to partially melt the rock, and now we're nudging it back towards that igneous realm. So there's some of the numbers there in terms of just how hot the rock needs to get. Below this number here, it's just not enough of an elevated temperature to cause a substantial change in most rocks. Where does the heat come from? It can come from magma bodies in the subsurface that are heating the surrounding rocks. It might come from rocks in a basin that are buried by more layers of sediment. As they get buried deeper and deeper, those rocks become hotter. It could be burial more related to a subduction zone where one plate is shoved beneath another. That's a good way to take rocks that were maybe close to the surface and get them down to a very deep level in a relatively rapid period of time geologically. And then the third one here, which is a minor one but still worth mentioning, is friction. We can get frictional heating along fault surfaces, or in a really exciting context, we can have meteorite impacts introduce friction into rocks and cause some change and metamorphism. So looking at the pressure that's exerted on the rock, there's two terms we tend to use. Confining pressure, where the rock's squeezed in all directions, all three directions, the rock is compressed, and that might happen in a basin as we load more rocks on top. The rock's squeezed top bottom, but it's also being squeezed left and right and front and back as well. And then in some unique instances geologically, we might have something called differential stress, or you could think of it as directional stress, where the pressure is greater in one direction than another. And this might take place at a convergent plate boundary where the plates are colliding. Might be some other situations as well, but that's probably the easiest one to consider. And when we have this type of stress in the rock, where the rock's being squeezed, kind of like imagine the rock being in a vise and being squeezed, the minerals within the rock are going to tend to, over time, rotate and line up perpendicular to that stress. And that lining up, or that arrangement of minerals in our metamorphic rock, is what we call foliation. So the layering you often see in metamorphic rocks is a different term than we use for sedimentary rocks. Remember, that was called bedding. It's actually called foliation. So we're going to look at a group of metamorphic rocks here in a bit that are foliated. So in this nice diagram down here, we have granite, which we've learned is made of different minerals, and they're all just sort of squished together into an interlocking mosaic, but there's no real fabric or texture or arrangement of the minerals in the rock here. But if this granite is squeezed at elevated temperatures, which allows the minerals to move and migrate, we might see more layering, crude layering in the rock and the resultant metamorphic rock. In this case, it's a metamorphic rock known as gneiss, and that would produce the foliation or the arrangement of the minerals you see there. So some fun terms here and ones that are pretty important as we study different rock types here in the metamorphic world. Here's just further illustrations to kind of hammer the point home. So this top left diagram here shows a basin, a bunch of layers here, and as we get down to the bottom of the layers, the rocks are being squeezed equally on all sides. So notice we've got arrows here on all sides, so that this is what we call confining pressure. Everything's just going to cause the rock to squeeze together. The particles have to get closer together. It's going to become more dense. You're going to reduce the porosity or the space between the particles. And then down here on the left, we have more of a situation where the rock's being squeezed preferentially in one direction. This is meant to show like a convergent plate boundary, which is producing mountains. And so the rocks here are being preferentially squeezed in this direction, and that's where we get the foliation. So we get the arrangement of the minerals here. And again, with the little circle here, confining pressure, you just squeeze everything together. And notice it's a circle, but if we preferentially squeeze it in one direction, like in the vise, we get more of an oval. And notice these little crystals, these black little lines here now are lining up more or less perpendicular to the stress that's being exerted on them. So what is the temperatures and pressures? We sometimes talk about metamorphic rocks in terms of low grade, intermediate grade, and high grade. And so there's some loose definitions that go along with this in terms of temperature ranges and pressures. It can differ from rock to rock, but this is generally a good guide. So a low grade metamorphic rock is one that's experienced temperatures in this range, intermediate grade, and high grade. And we can even sometimes work out what the depth was as well. So we can figure out, the minerals will record the temperatures that they form in, and then we can use that temperature to figure out the depth that the rock or the pressures that the rock formed in. So there's some really fun detective work that goes on that helps us determine the history of these metamorphic rocks. There's also some clues we can get by looking at minerals in our metamorphic rocks. So we've learned some of these minerals, not all of them, but we've learned in my mineral series we go over muscovite, biotite, and garnet. There's a few other ones in here we haven't covered. But this just shows low grade to high grade metamorphism, so increasing the grade, increasing the temperature across the metamorphic spectrum. This here in the middle is a list of a bunch of different minerals. We're familiar, of course, also with quartz and the two types of feldspar. And then down here at the bottom, we'll get to this more in a bit, but these are some of the rock names that you might see. So what this tells us then is if we can identify a mineral, if we can identify some of these minerals in our rocks, they might be useful in telling us something about the relative temperature or thermal histories of that rock. So for example, if I can see in my rock that I find that it definitely has some garnet in it, that tells me that it's an intermediate to high grade metamorphic rock, and that rock was exposed to temperatures probably from 400 degrees Celsius on up. So it was subjected to very high temperatures. Versus if I have something like chlorite or muscovite, those are lower temperature minerals. So there are minerals that can be good indicators for the relative temperatures that those minerals and subsequent rocks have experienced. So let's get into the names of the rocks. And again, at the Geology 101 level, these are the rocks that my students learn. There's obviously a lot more metamorphic rocks than this, but these are the ones that I introduced to them. So we start with the foliated metamorphic rocks, the rocks that are formed because of that uneven pressure that causes the minerals to rotate, and so we're getting layering in the rock. And you have to be careful because remember, sedimentary rocks have layers too. And so just because you see layering in a rock doesn't mean it's a foliated metamorphic rock. You have to convince yourself by looking at it closely that the minerals in the rock are aligned with the layering that you observe. So if you think that those minerals are following the layering there by looking at it closely, probably with a hand lens or maybe even a microscope, then there's a good chance that you're looking at a foliated metamorphic rock. But if you see some lines going through the rock and you look at it closely and the crystals just don't seem to have any sort of connection to that layering, then it's likely bedding or some other fabric that's running through the rock. So slate is our low-grade foliated metamorphic rock. Usually it's a shale or a mudstone that gets metamorphosed into slate. It can be tricky, especially when someone just hands me a rock and they say, is this a shale or a slate? It can be tricky. Out in the field, it's easier because you have context, right? So if you have a slate and then or if you have a layered, dull, fine-grained rock that you're not sure is a shale or a slate, but you look at the rocks maybe above and below it, if it's packaged together with other metamorphic rocks, then it would probably be appropriate to call it a slate. But if it's packaged together with a bunch of sedimentary rocks, it's more than often than not still a sedimentary rock also. So slate is, of course, what we've used to, if you think of old blackboards in classrooms, those are slate. The surfaces that pool tables are made of is slate in parts of the world. In Wales, for example, in the UK, a lot of the roofing material is slate because that's the local rock that they have there. So I've got a photo down here of slate. It's very fine grained, kind of dull colored, not shiny at all, usually some sort of earth tone in terms of color, but you can see it breaking along those foliation planes. So you can see that this rock preferentially has a direction it wants to break. So this is our first rock known as slate. As we increase the metamorphic grade a little bit, we get still a fine-grained rock, but now it's starting to have a sheen to it. It's a little bit reflective in the light. And it may have a bit of a wrinkly surface as well. And this is what's known as a phyllite or phyllite. Still the same parent rock, but we've increased the metamorphic grade just a little bit. We've kind of gone from the very low end of the metamorphic low grade spectrum. Now we're kind of up a little bit, not quite to medium grade or intermediate grade metamorphism, but we're getting close. So this would be a phyllite, something with a little bit of a sheen to it. And realize that this is a spectrum, right? You can, if you have something in between these two, it can be a tough call as to if it's a slate or if it's a phyllite. As we increase the metamorphic grade, the next rock is a schist. So here the mica crystals have grown large enough that they're visible. You should be able to see individual mica crystals. It'll be an extremely shiny rock. It'll be layered. It's foliated. So it's going to tend to probably form big, flat, planar sheets. And you may or may not see in your rock these large minerals called porphyroblasts. So for example, in this photo, we have some garnet porphyroblasts. Not all schists have this, but some do, which are these exceptionally larger crystals that form along with the rest of the rock. So this would be, again, this is a schist, and this would be what we might call a garnet schist because it has these big garnets in it. And then at the upper end of our foliated metamorphic rock spectrum is the rock we've talked about previously, gneiss. So now we've reached such high temperatures and pressures that the light and dark colored minerals, the felsic and mafic minerals, segregate into bands, and you'll see more of a layered appearance like zebra stripes. Micas usually don't are kind of on their way out, so there might be a few mica crystals, but not a whole lot. And the crystal size of these is a little bit more coarse grained. So there's our 4 foliated metamorphic rocks. And these could all be occurring within the same environment. So for example, here in the top right, if we look at a subduction zone where one plate dives beneath another, you might be cooking the sedimentary rocks at low temperatures and pressures into slate, and at higher temperatures and pressures into phyllite. And as you go deeper and deeper down underneath the mountains here in this convergent plate boundary, you could get schists and gneisses also as well. And then eventually you get to the point where the rocks may be melting a little bit as well, and you're generating magmas. And so here they are kind of shown here as well, just to kind of show you the spectrum. So this is one way to kind of compare and see all these together. I think it's helpful to see. The micas are very stable at these sort of intermediate grade temperatures. That's why the rocks get shiny right in here. But at the high grade temperatures, the micas are not stable. That's why you don't see those shiny minerals here when you get to metamorphic gneiss. 3 more rocks. So let's look at a few non-foliated metamorphic rocks. So rocks that will not show the foliation, the alignment of crystals within the rock. The first one here is marble. And the best way to tell these apart, especially in my 101 class, is by looking at the composition. So marble is totally made out of calcite. So my students can use the little acid bottles and test for that. Marble can be a lot of different colors. Pure marble is very white, but it can be pink. I've seen blue marble, gray, it can have banding in it, brown, all sorts of colors are possible. And this, of course, is limestone that's been metamorphosed. Quartzite is another metamorphic rock, and it can look a lot like marble. To me, it has a bit of a sugary texture, and I encourage you to look at some of my videos in the rock identification series to get a little bit more experience with this. But this is a sandstone that has been heated to the point where the sand grains are fused together. So rather than breaking around the grains like a sandstone does, that's why it feels so gritty, the cement and the grains are kind of one, and it breaks right through the grains. So it's going to have a smoother texture than a sandstone. It's going to be definitely harder than a sandstone. And yeah, and again, it'll have this kind of sugary texture, but somewhat difficult to tell from marble. If you kind of look at back and forth at these two, I mean, the color's a little different, but the color can vary with both of these as well. Quartzites can be many different colors. And then our final non-foliated metamorphic rock is a type of coal known as anthracite. It's black, shiny. It breaks along these little curvature surfaces here. From a distance, if someone just held this up from across the room, it can look a lot like obsidian. But unlike obsidian, which is made out of volcanic glass and is very hard and sharp, this is a rock made out of squished plants. It's a type of coal, and so it's going to be brittle. You might be able to bust off a little chip with your thumb. It's going to be lightweight, and so it's not going to scratch glass. It's going to have some very obvious properties when you hold it that let you know that it's actually not obsidian. So there's three non-foliated metamorphic rocks. Let's round up this episode by looking at a few different places where we see metamorphism occurring, and then I'll hit you with a few quiz questions here at the end. So environments in which we see metamorphic rocks created. So we have one such environment we call regional metamorphism, which is usually involved with plate boundaries. So if two plate boundaries collide, we thicken the crust, we bury rocks deeper, and that produces the right temperatures and pressures where we can have metamorphism occurring. So high pressures because the plates are squeezing together, relatively low to moderate temperatures mostly. I mean, it somewhat runs the gamut a little bit depending on how deep you are. But the temperatures definitely will be elevated because you've buried the rocks a little bit. And this is a good way to generate metamorphic rock over a large area, like a vast quantity and volume of metamorphic rock all at once. Another type of metamorphism is what's known as contact metamorphism. So here we would have a magma body, and the magma body is in contact with the surrounding rocks, and there are chemical reactions going on here. There's probably fluids moving through the rock, and so we would expect to see, due to the heat and maybe these fluids as well, a change in the existing rocks as we move away from the magma body, from a more substantial change maybe adjacent to the magma where the temperatures are higher, and then maybe here's some minerals that are more stable in this temperature realm, and then maybe another one out here. So we get this aureole that's developed around the margin of the magma body. This is a great place, and a place where a lot of exploration geologists and mining companies have focused. This is a place where you often find gold, silver, copper, other valuable resources concentrated. As if you have a magma body invading, especially like a sedimentary rock or a rock that's very different than the magma, and you're getting these chemical reactions going on here. So obviously this would be very high temperature. You have magma, but these are relatively shallow, so the pressures are quite a bit lower. Burial metamorphism is just where we have rocks that are buried underground. So if you consider that in most places, the average geothermal gradient, basically how hot does the earth get with depth. So if you go down 1 kilometer, on average, the rocks heat up about 25 degrees Celsius, about, I don't know what that is Fahrenheit, like 70, 80 degrees Fahrenheit, something like that. And so you have to get all the way down to about 8 kilometers, about 5 miles or so, in order to even get low-grade metamorphism occurring. And now this is average gradient for average across the earth, right? So this might be going to someplace like, I don't know, the middle of the US, like Nebraska, where there's no obvious heat source underground other than just the regular heat, the background heat of the earth. But if you go to a geothermal area or a place like Yellowstone, shown here, you can get metamorphism occurring at much shallower depths because it's obviously a hotter environment. The heat is closer to the surface, and so therefore metamorphism might be occurring at much shallower depths than we see otherwise. So generally with burial metamorphism, pretty low temperatures and pressures. You're burying rocks in a sedimentary basin or something like that. This one's just a sexy one to include, so I include it, and that is impact metamorphism. Probably not that common, but it's an exciting story, so it's fun to talk about. So this would be, collisions from meteorites or other objects in space hitting the Earth at very high speeds, exerting and creating extremely high temperatures and pressures, and actually causing changes to the existing rocks. This is where we get, maybe you can get the diamonds depending on if there's carbon in the site that's impacted. There's a fun type of quartz called coesite that forms from this as well. So not very common, but a fun one just to think about, and definitely one you could explore a bit on your own if you're interested. All right, let's do a couple of quiz questions here to round out this episode. So this question here, which metamorphic rock sequence listed below is correctly arranged from high grade to low grade? So look at the 5 lists there, and go ahead and pause the video if you need to. Okay, so we want to go from high grade to low grade, and we have 4 rocks that we've just learned. These are 4 foliated rocks. Well, our high grade rock, if you remember, the rock that forms at very high temperatures and pressures is gneiss. So that's going to make it either C or D. And as we move down to lower temperatures and pressures, the next one is schist, then phyllite, then slate. So C was the best answer there. How'd you do? Hopefully you did okay. If you did well, give yourself a gold star. If you didn't do well, just learn and do better next time. So here's a cross section, and so let me explain the cross section. This is a slice through the Earth. Rock unit A and D are igneous rocks, but all the other rocks, C, H, E, G, F, B, let's say that those are all sedimentary rocks, sandstones, limestones, mudstones, things like that. So the question is, in this cross section, which unit of those ones listed did not experience contact metamorphism? So go ahead and pause the video if you need some time. Study the cross section, take a look at it, and then we'll go to the big reveal. So remember, contact metamorphism is where magma is in contact with the existing rocks that are there. So we could say then that around this magma body D, there is contact metamorphism that has occurred around the margin of this, and that would have cooked to some degree or metamorphosed H, parts of E, G, and F. Likewise with this magma body over here, it would have done some contact metamorphism to C, H, G, maybe F, and then the same ones on that side. But the one unit that kind of stayed above it all, now you could argue that we don't know how close this is to B, but the one unit that is not in direct contact with what was once magma is unit B. So that would seem to be the best answer based on what we know there. Okay, and then here's our final question. If you're enjoying the quiz, here's your last question. So let me explain the diagram here. I have a simple graph showing temperatures ranging from low temperatures to higher temperatures. And here on the y-axis is depth, shallow depths to deeper depths down into the Earth. And so of the 4 circle choices here, A, B, C, D, which of the ones best matches the conditions that you'd expect to find related to contact metamorphism? So go ahead and pause the video if you need to. Okay, so remember, contact metamorphism is magma in contact with the surrounding rocks, so that would put us at high temperatures. And generally, those conditions are going to take place at fairly shallow levels in the Earth's crust. So that's going to put us somewhere in this region in here. Generally, you don't see these magma bodies this far down, although they can sometimes. So the best answer in this case would be B, this one right here. Again, these questions aren't perfect and you could quibble with them, but I do teach my students to just kind of stick with some of these broad themes. Contact metamorphism is generally a high temperature, low pressure, or low depth, shallow depth type of condition. So hope you did well. Hope you enjoyed this episode on metamorphism. Look for our next episode soon. And thank you for your support of the channel. If you'd like to donate, there's a thanks button below the right of the viewer. There's also some links under the video description where you can donate to the geoscience education videos I put together. But thanks for joining me on this one, and we'll see you next time. Take care.